guys, welcome to our new video on stereochemistry. Today we're going to talk about the classification of stereoisomers, and later we will discuss the conformational analysis of alkanes. So let's see how stereoisomers are classified. In my previous video lecture, I have told you about how we can classify stereoisomers. So there are two major classes of stereoisomers, and these classes are purely made on the basis of the energy barrier or the difference of energy barrier between different isomers. So it is only the difference in the energy barrier for the conversion of one isomer into another stereoisomer that differentiates one class of stereoisomers from another class of stereoisomers. And the kinetic stabilities of these different types of stereoisomers depend only on the height of the energy barrier. Now, the height of the energy barrier means primarily the energy that is required for the conversion of one stereoisomer into another stereoisomer. Or you can say that one stereoisomer has to cross an energy hill. It has to climb an energy hill before it can convert into another stereoisomer. So the higher that hill, the higher is the difference between the energies of the two stereoisomers, and the difficult it is to convert one stereoisomer into another. And when it is difficult to convert one stereoisomer into another, or the height of the energy barrier is much higher, it means that the two stereoisomers are kinetically quite stable, so you can have them separately and you can study them separately. On the other hand, if the height of the energy barrier is not much, it means they can easily interconvert into each other, and in that case it may not be possible for you to isolate them separately or to study them separately. So the two major classes of stereoisomers are the conformational isomers or the configurational isomers. Conformational isomers are also known as conformers. Now let's see how we can differentiate between configurational and conformational isomers. So first thing first, configurational isomers are separated by a higher energy barrier that is usually more than 100 kilojoules per mole. It means it requires more than 100 kilojoules per mole of energy to convert one configurational isomer into another configurational isomer. On the other hand, the energy barrier between two conformational isomers is quite low, and that is usually below 60 kilojoules per mole. So from this data you can say that the interconversion of two conformational isomers is quite easier as compared to the interconversion of two configurational isomers. And it is only because of the higher energy barrier between two configurational isomers that they are quite stable. And stability means that they can exist as separate entities, and in the same way they are separable at room temperature. This means that you can have them separately, you can study them separately, you can study their properties separately, because the energy barrier is higher, so they can exist as separate stereoisomers which can be studied for their different properties. On the other hand, conformational isomers, because they have a lower energy barrier, they are easily convertible at room temperature. And this means that they are relatively less stable as compared to configurational isomers. which means that they are not separable at room temperature, and which means that you cannot have them separately and you cannot study them separately. So this is how we can differentiate between conformations and configurations. And now we'll discuss conformational analysis of alkanes in more detail. But first, conformations are actually the various shapes that are available to a molecule or that are adopted by a molecule just by rotation around a carbon-carbon single bond. So conformations are the different shapes adopted by a molecule when the different groups rotate around a carbon-carbon single bond, or there might also be other changes involved apart from rotation around this carbon-carbon single bond, which may lead to the conversion of one conformational isomer into another conformational isomer. But these changes do not involve bond breaking. We've already seen that the energy barrier between two conformational isomers is usually less than 60 kilojoules per mole, or it is quite low, but bond breaking requires higher energy. So the interconversion of two conformational isomers do not involve bond breaking, but it may involve single bond rotation or rotation around a single bond, along with some other changes that may convert one conformer into another conformer. And it is because of this rotation around a carbon-carbon single bond that these conformational isomers or conformers are sometimes also known as rotamers. So this conformational process, or the conversion of one conformational isomer into another, have relatively lower energy requirements and they are easily interconvertible. What are the examples? Let's see on the next page how we can explain different conformational isomers. So we start off with ethane. Ethane is a simple molecule that has two carbon atoms, and each of these carbon atoms has three hydrogens attached to it. Now, both the carbon atoms are sp3 hybridized, which means that the geometry around each of these carbon atoms is tetrahedral geometry. Now, to analyze ethane for its conformations, we have to draw a Newman projection for this molecule. And in my previous video, I have told you how to draw Newman projection. For Newman projection, you have to weave the molecule from one end through this carbon-carbon bond and then draw the groups relative to each other that are attached to both the carbon atoms. So the carbon that is closer to you is shown as a dot right here, and the carbon that is away from you, if you are looking from this side, this is closer to you and this carbon is away from you. So this is shown as a circle. Now the one that is closer to you has three hydrogens attached to it, which are shown with a blue, purple, pink and a red color or bond, and the carbon atom that is away from you, or the one that is shown with a circle, also has three hydrogens shown with a red, a pink and a blue line. Now this is the Newman projection for ethane, and we have drawn this in a way that all the hydrogens are away from each other in space. And such type of a conformation is known as a staggered conformation, in which all the hydrogens or all the groups, whether they are hydrogens or anything else, they are away from each other, right? Now, how they are away from each other? The dihedral angle between these two hydrogens, which are colored with blue is about 60 degrees. You see, if you take it as a full circle, a circle has 360 degrees. So this is 60, 120, 180, and then we have the rest of the three angles, and then the full circle, right? So the angle between these two hydrogens is about 60 degrees, and this angle is known as the dihedral angle. What is a dihedral angle? I will tell you in a couple of minutes in the next slide what a dihedral angle actually means. Now, this conformation is known as the staggered conformation. Now, what we do is that we keep one of the carbon atoms, whether that is the dot or the circle, fixed in its position, which means that the groups that are attached to it or the hydrogens that are attached to it do not change their positions, and we rotate the other carbon atom. Now in this case we have kept the front carbon or this carbon fixed, so the groups, the hydrogens that are attached to this carbon does not change its position through the process, and we rotate the rear carbon or the carbon that is shown with a circle through different angles. So what we do is that we keep this carbon fixed and we rotate this circle or the rear carbon through 60 degrees clockwise. So you see, if you rotate this circle clockwise through 60 degrees, what will happen is that this hydrogen, this blue hydrogen which was here initially, goes through 60 degrees, and now it will lie right behind this hydrogen here. I have just drawn it on a side just to tell you that this hydrogen is present here. It actually is right behind this hydrogen, but in that case you won't see it, so I've just drawn it on a side so that you can see it clearly. And because this has moved 60 degrees, this hydrogen in the red is also attached to the circle. It will also move 60 degrees clockwise, and it will lie, or it will end up right behind this red hydrogen here. This pink hydrogen will move again through 60 degrees clockwise, and it will end up right behind this pink hydrogen. And now you see that the three hydrogens attached to the circle or the rear carbon are eclipsed by the hydrogens present on the front carbon atom, or the three hydrogens on the circle are right behind the three hydrogens on the front carbon. So we say that it is an eclipsed conformation. Why we say that it is an eclipsed conformation? Because the hydrogens are right in front of each other. All the hydrogens are in front of each other. Now what we do is that we give it another 60-degree clockwise rotation. So when you rotate this circle clockwise through 60 degrees, this blue hydrogen will come here. You see, it is here. This red will rotate through 60 degrees, so it will come here. You see, this hydrogen, the red hydrogen with the circle, is now here, and this pink hydrogen on the circle will end up here. So you can see it is here. And again, all the hydrogens are away from each other, just like this one. So this again is a staggered conformation. You give it another 60 degrees rotation, and the hydrogens will be eclipsed, just like this one. You give it another 60-degree rotation, they will be staggered again and again and again until you reach this final staggered conformation or initial conformation. But in this case, in case of ethane, because all the groups are similar to each other, both the carbon atoms have 6 hydrogens attached to it. So all the atoms attached to these two carbon atoms are similar. So no matter where they lie, they are the same. We have just drawn them here with different colors just for your understanding. Otherwise, they are the same hydrogen atoms, and whether they are in red color or blue color, it doesn't make any difference. So this staggered conformation actually is very much or is exactly the same as this staggered conformation, and this is an eclipsed conformation that is different from the two. Now, what is the difference between these staggered and eclipsed conformations? You see, these hydrogens are away from each other in space, and so there is lesser or almost no steric hindrance between them. So when there is no steric hindrance between the groups in a molecule, it usually is quite stable. So this staggered conformation is a stable conformation of ethane. But when you rotate it through 60 degrees, the hydrogens come closer to each other in space. They are eclipsed now, so they are closer in space, and they might experience some steric hindrance. And then you could rotate it again through 60 degrees to get a staggered, more stable conformation. So to go from one staggered conformation to another staggered conformation, this ethane molecule has to pass through an eclipsed conformation. And this eclipsed conformation is just like a transition state for the conversion of one staggered conformation into another staggered conformation. Now, it doesn't happen really that ethane would sometime exist as staggered, or sometimes it will exist as an eclipsed conformation. Or when you take one sample of ethane, it will have staggered ethane molecules, or in another sample it will have eclipsed ethane molecules. No, the molecule always, no matter what it is, it will always try to exist in the most stable conformation, or in the most stable of the geometries. So ethane will mostly be present in a staggered conformation. And as we have already discussed that the energy barrier is very much lower, the molecule exists as a dynamic system. So this molecule is usually rotating around this carbon-carbon single bond, and it is having staggered and eclipsed conformations from time to time, but it will spend most of its time in the staggered conformation. So it will usually be present, or you will have to consider this ethane as a staggered in a staggered conformation, not in an eclipsed conformation. And this system consists of different species like this, which are in equilibrium, and they continuously change their geometries. So you can see they are in a dynamic system, and they are changing their geometries from time to time after rotation through a particular angle. Now here you may ask a question that whether ethane has only these three conformers, or only two conformers, a staggered and an eclipsed conformation. No, it can have innumerable number of conformations or conformational isomers. So you can rotate this carbon atom through 1 degree, through 2 degrees, to 0.5 degrees, through any angle, through any degree, and you will get a new conformational isomer of ethane. Then why we are discussing only these two or three conformational isomers? It is because they are the most important, or they are the least energetic and the most energetic isomers. So that's why we are discussing these two stereoisomers or conformational isomers. Otherwise it can have infinite number of conformational isomers just by rotation through any degrees in this 360 degrees. So this is the energy profile diagram of ethane. So we have energy on one axis and the torsion angle on another. So we start off with the 0 degrees, in which the hydrogens are eclipsed. There's 0 degree angle or dihedral angle between the hydrogens attached to the front and the rear carbon atoms, and because they are eclipsed or closer to each other in space, that is why this is a higher energy conformation. And then rotation through 60 degrees will convert this eclipsed conformation into a staggered conformation, and that will lower the energy of the system and the energy goes down. And then another 360-degree rotation will take it higher, another 60-degree rotation will take it lower, then a 240-degree rotation, a 300-degree rotation, and finally a 360-degree rotation will give you the original molecule. Now, because both the carbon atoms in ethane have only hydrogens attached to it, the energy difference between these two conformations and these two conformations is the same. So it usually is about 12 kilojoules per mole difference between a staggered and an eclipsed conformation of ethane, and that 12 is because of the 3 eclipsing hydrogens. So if you divide it by 3, it means that eclipsing of one hydrogen by another hydrogen increases the energy or elevates the energy by about 4 kilojoules per mole. So there is eclipsing of 3 pairs of hydrogens, and that is why the total energy rise for the in conversion of one staggered conformation into eclipsed conformation is about 12 kilojoules per mole. So it means that the conversion of one staggered conformation into another staggered conformation will require this molecule to rise or to go up an energy barrier of about 12 kilojoules per mole to convert into another staggered conformation. So this was all about ethane. Now we discuss another case of alkane, that is butane. So butane has 4 carbon atoms in a chain, and we will discuss the different conformations possible for butane. Now when you have a longer chain, you can select any of the 2 carbon atoms as the front and the rear carbon. But in this case, in case of butane, if we take the carbon number 2 and carbon number 3 as our front and rear carbons, it will give us a better and a clear picture of the different conformations possible for butane. So what we have here is a CH3 attached to a CH2, which is then attached to another CH2, and which is attached to a CH3. So we have 1, 2, 3, and 4 carbon atoms. We have taken carbon number 2 and 3 as the front and the rear carbon, or the dot and the circle carbon atom. We start off with this conformation in which you see all the groups are staggered with reference to each other. They are away from each other in space. Unlike ethane, in which each of the carbon atoms, the front and the rear carbon, had 3 hydrogens attached to it, here our front and rear carbons have 2 hydrogens and a methyl group attached to it. So this is slightly different from that of ethane. But in this case, you see that all the groups are staggered. And another interesting point in this case is that we have a bulkier group attached to this carbon atom as well as to the rear carbon atom, or the one that is shown with a circle also has a bulkier CH3 group. Now in case of hydrogens eclipsing hydrogens, the steric hindrance will be lower, but when we have a bulkier group, this steric interaction increases. So these CH3 groups will experience, or they will offer more steric hindrance when they come closer to hydrogens or when they come close to each other. So they will try to be at maximum distance from each other. So in this case, the maximum distance could be that when they have a 180 degrees angle between them. So now you see they are exactly on opposite sides of each other, having a 180 degrees angle between them. This type of conformation is known as the anti-staggered conformation. In case of ethane, we had only one type of staggered conformation, but in case of butane, we can have different staggered conformations. The first one, in which these CH3 groups are at maximum distance from each other or at 180 degrees from each other, is known as the anti-staggered conformation. This anti-staggered conformation sometimes is also written as or known as anti-periplanar conformation. Again, we keep one of the carbon atoms, the front carbon in this case, fixed, and rotate the rear carbon or the circle through 60 degrees. So when you rotate this circle through 60 degrees clockwise, this CH3 in red goes through 60 degrees and it ends up here behind this hydrogen. So again, I have shown it slightly to a side just to let you know that there is a CH3 right behind this hydrogen. Otherwise you won't be able to see it. So this CH3 goes through 60 degrees to end up right here behind this hydrogen. As a result, this hydrogen also rotates clockwise through 60 degrees to end up behind this CH3 in the blue, and this hydrogen ends up here behind this hydrogen. Now you see all the groups are eclipsed. But unlike ethane, which had only one eclipsed conformation, butane again can have different eclipsed conformations. We have all the groups eclipsed, but the bulkier groups, the CH3 groups, are eclipsing the hydrogens in this conformation. So we say that the groups are eclipsed, but the bulkier groups are eclipsing the smaller hydrogen atoms. So this CH3 is eclipsing the smaller hydrogen atom. This CH3 has been eclipsed by the smaller hydrogen atom, and these two hydrogens are eclipsing each other. So they are eclipsed, but they are partially eclipsed, and such type of a conformation is sometimes also known as the anticlinal conformation. Then we rotate it again through 60 degrees. So this CH3 will end up here, hydrogen will end up here, and another hydrogen will end up here. So again, we have a staggered conformation, or all the groups are staggered with reference to each other. But this is different from the anti-staggered conformation. Why? Because now the two bulkier groups, the CH3 groups, are closer to each other in space, and you can see it clearly here. The dihedral angle between the two CH3 groups is 60 degrees. Here it was 180 degrees. They were at maximum distance from each other. Here the dihedral angle was 120 degrees, and now the dihedral angle is 60 degrees. So no doubt they are staggered with reference to each other, but because the bulkier groups are closer to each other, it will be a slightly higher energy conformation, and we call it a gauche staggered conformation or a synclinal conformation. And when we rotate it again through 60 degrees, you will see that this CH3 ends up right behind this CH3, and this is a disaster. Why? Because now we have the two bulkier groups in the molecule, the two CH3 groups right behind each other or in front of each other. They are eclipsing each other, and this conformation means that the groups experience the highest steric interaction or steric hindrance. And now, because the two CH3 groups are eclipsing each other, the hydrogens are eclipsing each other, we say that it is a fully eclipsed conformation or a syn periplanar conformation. And because the bulkier groups are eclipsing each other here, this fully eclipsed conformation is the highest energy conformation. And then we rotate it again through 60 degrees. So this red CH3 comes here. It's a staggered conformation, and just like this one, in which the two CH3 groups had 60 degrees angle, dihedral angle between them, here again they have a 60 degrees dihedral angle between them. So it's a gauche staggered conformation, or again a synclinal conformation. And when you rotate it again, the CH3 will come here, and the hydrogens again will eclipse each other. So we will have a partially eclipsed conformation, and when you rotate it again, the CH3 will come here, and you will get the anti-staggered conformation back. So all these conformations are interconvertible by rotation through 60 degrees. And again, I repeat myself that these are not the only possible conformations for butane. Just like ethane, which had infinite number of conformations possible, the same is true for butane. You can rotate the molecule or the carbon atom through 1 degrees, to 2 degrees, 3 degrees, 0.5 degrees, through any angle, and you will get a new conformational isomer. But these are the most important or the lowest or the highest energy conformations. That is why we are discussing them here. So this is the energy profile diagram of butane, and it looks different from that of ethane. In ethane, we had one energy maxima and one energy minima, having equal energy difference between all of the conformations, but this is not the case here. So we start off with the syn periplanar conformation, in which the two methyl groups are eclipsing each other, and as I told you, it is the highest energy conformation. So the energy lies right up here, and then when you rotate the molecule through 60 degrees, the groups are staggered, but the methyl groups are closer to each other. It's a synclinal or gauche staggered conformation. The methyl groups are closer, they are at 60 degrees dihedral angle, but because the groups are staggered, the energy goes down. And then you rotate it again through 60 degrees, you will get eclipsed conformation, so the energy should go up. But the energy does not end up here equal to the energy of the syn periplanar conformation, but it is slightly lower than this. Why? Because in syn periplanar, the two methyl groups, the bulkier groups, were eclipsing each other, so this was the highest energy conformation. This anticlinal conformation has eclipsed groups, but the methyl groups are eclipsing the hydrogens, not each other, and that is why the steric hindrance is relatively lower as that in syn periplanar conformation. So it's a energy hill, but not as steep or as high as the syn periplanar conformation. And then you rotate it again through 60 degrees, the energy goes down, because now we have a staggered conformation or an anti-staggered conformation, or the anti-periplanar conformation, in which the two methyl groups are at maximum distance from each other, that is 180 degrees, and this is the lowest energy possible for all the conformations of butane. Now the energy difference between this anti-periplanar and syn periplanar conformation is about 25 kilojoules per mole, and the energy difference between anti-periplanar and anticlinal conformation is about 14 kilojoules per mole. So the difference is of about you can say 11 kilojoules per mole between anticlinal and syn periplanar conformation. So from here, if you rotate it again, we have a eclipsed conformation in which the methyl groups are eclipsing the hydrogen, so it's an anticlinal conformation. The energy goes up, and it is the same as that of the first eclipsed conformation right here. When you rotate it again, we have a synclinal or a gauche staggered conformation whose energy is exactly similar to this conformation, and finally we rotate it again through 60 degrees to get the syn periplanar conformation. So we have two energy maxima and two energy minima in case of butane. So the difference in energy between gauche and anti-conformers of butane is phase dependent. So it depends upon the phase of the molecule, how much energy difference would be there between the gauche and the anti-conformers. Now, you saw that butane has different conformations: the anti-staggered, the gauche staggered, the synclinal, the anticlinal conformations, or the anti-staggered or the fully eclipsed conformation. The overall molecular volume is different. If you just imagine the molecules, the molecular volumes are different for all of them, for some of them. And because of the different molecular volumes of these different conformations, they exhibit variation in their properties, such as the densities, the heat of vaporization, the refractive index, and even the boiling points are different for these different conformers of butane, only because of the difference in their molecular volumes. So guys, this was all about the conformational analysis of alkanes. We discussed ethane and butane in quite detail. In the next video, I will we will discuss the conformational analysis of cyclic alkanes or cycloalkanes. So stay tuned and wait for the next lecture. Thank you so much.